Hi everyone, welcome back to Timates. So in my last lecture, I have talked about the instability of the atomic structure due to emission of electromagnetic radiation caused by movement of the electron in a circular orbit, where it is accelerated. But I have not uh, talked about the physical properties and the origin of the electromagnetic radiation in details. So actually the basic understanding of electromagnetic radiation is required to understand the structure of the atom. So in this lecture, I will initially talk about the basic theories of electromagnetic radiation and its properties, and then I will talk about another drawback of the Rutherford model. So what is electromagnetic waves? So in simple language, electromagnetic radiation is one of the many ways that energy travels through space. The heat from a burning fire, the light from the sun, the X-rays used by your doctor, as well as the energy used to cook food in microwave are all forms of electromagnetic radiation. While this form of energy might seem quite different from one another, but all of they exhibits wave-like properties. So when I told wave-like properties, then the next question comes, what is wave? So although I guess all of you are familiar with what is wave, if you have ever gone swimming in the lakes, ponds, or river, you are already familiar with waves. Waves are simply disturbances in a particular physical medium or a field, resulting in a vibration or an oscillation. The swell of a wave in the ocean and the subsequent dip that follows, it's simply a vibration or oscillation of the water at the ocean surface, right? So that means oscillation of medium is required to create waves, right? So now the next question is, then what is creating electromagnetic radiation? What is oscillating here? Actually, the oscillating electric field or accelerated charge particle is created electromagnetic radiation. Why I am saying this? Because let's say, according to this picture, let's say I have a electric field in this y direction, okay, and it is oscillating in a y direction like this. This is my electric field vector. This is x, but this is in y. It is oscillating only in the y direction. Okay, so and this is it. Exactly like this picture. Okay, so let's say in this instant it's directing towards plus y direction. Okay, this is electric field vector, and after some time it is directing in this direction. So that means this is electric field is varying with time, right? We know that so in this direction, if electric field is in the upward direction, plus y direction, the current will flow in the opposite direction, that is in minus y. So electric current will, for this orientation of electric field, current will follow in this minus y direction. And in this case, when the electric field is minus y, current will flow in the plus y direction, right? This is the general convention that we follow. So along with this electric field, the current is also changing its direction, right? So we know from the electromagnetic theory that when current changes with time, it also creates a magnetic field along with it. So this current, changing current actually also creates a magnetic field, but in which direction that magnetic field is created, it is created exactly in the perpendicular of the direction of the electric field. Right? So that means it's just look at this picture carefully. So this electric field is actually created in this your z direction. It's perpendicular to the y, right? So it's also perpendicular. Y and z are perpendicular, and a magnetic field is created in the z direction. Okay. So we have two inseparable fields, two inseparable oscillating field. One is electric field, and the other is magnetic field. Separating oscillating field, perpendicular field. Let's say. Okay. So these two inseparable oscillating electric and magnetic field creates electromagnetic radiation and or the light. And then what is the propagation direction of the light? It is in the x direction, that is perpendicular of both electric field vector and your magnetic field vector. Okay, this B. So that's how light is created. So we have understand the origin of the electromagnetic waves. Now we will learn about some of its basic properties. So yep. Okay, distance. Okay. So you might already know that a wave has a lowest point as a highest point, right? This is the highest point of a wave. This is the lowest point. Okay. The vertical distance between the tip of a highest point and the wave's central axis is known as its amplitude. So this is the amplitude of the wave. Okay. This is the property associated with the brightness or intensity of the wave. Okay, actually, intensity of the light proportional to amplitude square. Amplitude square. Okay. Okay. The horizontal distance between two consecutive highest point or the lowest point is known as the wavelength of the wave. It is the wavelength. So that means this horizontal distance between the lowest point, that is this to this, is the wavelength, or distance between to the highest point is also called a wavelength. This is also wavelength. These two are same. Okay, distance wise. Okay. Now, the formal definition of wavelength is given as distance covered per oscillation. Okay, what do we mean by a complete oscillation? Complete oscillation means the point that emerges as its initial point. That means if the waves start from this zero, when it goes to zero after a full cycle, it's called a complete oscillation. That means one wavelength distance means one complete oscillation. One wavelength is given as sin lambda equal to one complete oscillation. Now, so wavelength is distance covered per oscillation. So that means distance covered per oscillation. Okay. Another important term is your frequency. What is frequency? It is the number of oscillation per unit time. It is number of oscillation per unit time. Okay. So another important relation that relates frequency and wavelength is the speed of the light. Okay. So again, is general. How can you define the speed? Is the distance covered by light per unit time. Distance covered by light per unit time. So in per unit time, how many oscillations are there? It's its frequency. So what is speed? Speed is the distance covered by light per unit time. So that means your number of oscillation per unit time multiplied by distance covered per oscillation, right? So let's say speed we denoted as C. What is the number of oscillation per unit time? It is your frequency, and distance covered per unit second. This is your wavelength. So this is one important relation. The speed of the electromagnetic radiation is equal to its, or any wave is equal to its frequency and wavelength. Actually, this relationship reflects an important fact. All electromagnetic radiation, regardless of wavelength, different wavelength or frequency, travels at the speed of the light. So the kind of electromagnetic radiation that I already mentioned in the example, that is your sunlight or your microwave, radio wave, all may have different frequencies or wavelength, but all moves with the same speed. Okay. Another thing that differs, that differentiate electromagnetic wave with normal wave is for propagation of electromagnetic wave, we don't need any medium, but for the propagation of our normal wave, we need some medium, right? Electromagnetic wave can still travel without any medium. These are the some important facts. So, by the way, sorry, I forgot to tell you one thing. Another relation is that is the wave number. This might need it. Wave number is the number of wave per unit length. This wave number per new part, it is number of wave per unit length. So if we say up to this distance, if this is 1 unit, if up to this distance is 1 unit, then what is the wave number? It's 1. That is here, as here is only one wave is present, so it is called wave number. Okay. So what happens when wave numbers are large? That means highest point, the oscillation will increases, right? So if wave number are large, that means large number of waves are present in the certain distance. So that means large wave number. So that means what? Number of oscillations is also increasing. So wave number and frequency are directly proportional to per is frequency proportional to wave number. So frequency is proportional to wave number. Again, if we see the definition of wave number and wavelength, it is clear that they are basically reciprocal of each other, because wavelength means distance traveled by a wave per oscillation, and wave number means number of wave per unit length. So they are basically reciprocal of each other. So again, we know, so basically mu is mu equal to 1 by lambda or wavelength. We and lambda and c are related by this relation. So we can write lambda equal to c by nu from this here. So wave number is frequency by speed of the light. Okay. So till this point, we have learned about the variables that describes the electromagnetic wave. Now we will learn about the electromagnetic spectrum in the next section. Okay. So what is electromagnetic spectrum? Electromagnetic waves can be classified and arranged according to their various wavelengths or frequencies. This classification is known as the electromagnetic spectrum. The following table shows us this spectrum, which consists of all types of electromagnetic radiation that exist in our universe. Okay. So as we can see, the visible spectrum, that is the light we see with our eyes, makes up only a small fraction of the different types of radiation that exist. This one up. Okay. So to the right of the visible spectrum, we find the types of energy that are lower in frequency, this part, and this type of energy. So these are the lower in frequency and there's a lower in wavelength than visible light. This type of energy include IR rays, that means the heat waves given off by thermal bodies, microwaves and radio waves. This type of radiation surround us constantly, and these are not harmful because of their frequencies are so low. We will learn in the following sections that if energy of the electromagnetic radiation is proportional to its frequency. Just after this finishing of this, I will talk about it, why this proportionals and all. I will explain everything. But right now, just take it as a statement that energy of electromagnetic wave increases with its frequency, and it is inversely proportional to its wavelength. So this the waves that lies in the right hand side of this visible light, or that means whose frequency is low than visible light, so its the energy is low, that's why it is not harmful. On the other hand, if we go to the left side, this series contains X-rays, UV rays and gamma rays. This type of radiation are harmful to living organisms due to their extremely high frequencies and thus extremely high energies. Okay, so in the next section, we will talk about the relationship between the wave's frequency and its energy. For this, we need the concept of quantization of energy and the dual nature of light. Okay, so we have already discussed how light travels through space as a wave. This has been well known for quite some time. In fact, Dutch physicist Christian Huygens first described the wave nature of light as far back as late 17th century. Physicists actually thought at that time that light waves and matter are quite distinct to each other. According to classical physics, matter composed of particles that has mass and whose position in space is well known. So if we see a particle, it has some mass, and let's say its position with time, and it has some well definite position. So we know that there's a way we can track its position at every time. It's a measurable quantity. So at time t1, it's in this position. At time t2, it is in this position. That's all. Okay. So light characteristics of matter is it has some definite mass, and his position in space is well defined. Light, on the other hand, is considered as zero mass, and its position in space uh, cannot be determined because waves is a diverse thing. So up to this point, it's a complete wave. So if someone tells you what is the position of the waves, it has not definite position. Can we tell its basic position? No. It is spread over in this region. If it is 0 and this is x, the whole area, the whole length is its position. Right? So wave is so position of the wave cannot be determined. Okay, we have to always tell it by its range or by its wavelength. Because waves and matter are considered to be in different categories. Scientists did not have a good understanding of how light and matter interacted. So these all changed in year 1900 when physicist Max Planck began to study black bodies. So a black body means a body that emits all the radiation that it absorbs. Actually, a very hot object, it's sometimes is regarded as a black body. So what is so interesting in this black body? That Planck found that the electromagnetic radiation emitted by black bodies could not be explained by classical physics, which postulated that matter could absorb or emit any quantity of electromagnetic radiation. Planck observed that in black body, matter actually absorb or emit energy only in discrete amount. So that means delta E equal to N into E, where N equal to 1, 2, 3, etc. So this only this integer value of N poses a restriction on the energy exchange in the black body, because then energy cannot be absorbed or emit in any amount. It has to be whole number of multiple of this small quantity called E, right? So what is this E small? What is this value of E? So this E is actually called energy quantum. Means it's the minimum amount of energy that can be transferred. Okay, so and this E is actually equal to h nu, where nu is the frequency of the radiation, where h is the Planck's constant and nu is the frequency of the radiation. What is the value of h? So value of h is 6.626 into 10 to the power minus 34 joules again. It's very, very low. Okay, joules second, joule second. Okay, but actually this is a shocking discovery because it changed the idea that energy was continuous and could be transferred in any amount, like this picture. Okay. The reality which Planck discovered is that energy is not continuous but the quantized, meaning that it can only be transferred in individual packets of size h nu. Each of this energy packet is known as quantum. So while this might sound confusing, we are already very familiar with this quantized system. The money we use daily, for example, is quantized. For instance, when you go to a shop, you will not see anything on sale for a price, say 50.078 rupees. You cannot say something is selling in this price because smallest possible monetary unit is your 1 rupees. Anything below 1 rupees, you cannot pay anything at the moment. I don't know whether 50 paisa is still valid or not. But let's say now for this case that okay, so 1 rupees is the smallest monetary unit. So it is impossible to transfer the money in any smaller amount than this. So just as we cannot pay the shopkeeper at that half of a paisa or fraction of a half of a rupees or fraction of a rupees, that means we cannot pay half rupees or 1/4 rupees. Energy cannot be transferred in anything less than a single quantum, that is h nu. Less than this amount, energy cannot be transferred. So we can think of this h nu as being like this 1 rupees, the minimum monetary unit. So the smallest possible value by which the energy can be transferred, that is h nu. Smallest of energy that can be transferred. Okay. Few years after the Planck's discovery of discrete energy level in case of black body, few years later, the phenomena like photoelectric effect, Compton effect, proved that light is a collection of small massless particle called photon, which has energy equal to h nu. And again, this is the minimum energy of photon that is h nu. Again, h is a Planck's constant and is the frequency of the electromagnetic radiation or light. So when photon is actually photon can be absorbed or emitted by a species. It like the not necessarily its atomic molecule. It can be absorbed by emitted by any body, any species. So, but again, this minimum energy that a photon can transfer to a body is h nu. Nothing more, nothing less. Okay. So let's say there is a body A. When light falls on it, and so that means light gives an energy equal to h nu on it. So then it moves to any star called A star. It got excited. So it can be seen from this picture as well. Let's say this initially before light falls on it, its energy is E1. After light falls on it, it absorbs this h nu amount of energy, and it will absorb h nu amount of energy, nothing more, nothing less, because and it goes to E2 state. Okay. Presently light, it goes to E2 state. Now the question is, can it go? Let's say there is another state that is present between this 1 and 2, that is 1 dash. Now the question is, can this particle goes to 1 dash state? The answer is no, because The minimum possible amount of energy that can be transferred by photon is h nu. So if one dash is one dash is basically somehow midway between 1 and 2. So the required frequency that will require to transfer the energy is h nu by 2, which is not possible because minimum, just like in the previous example, we told that half of a paisa cannot be transferred. Okay, how it cannot be, I mean, transferred in a shop in Indian market. So similarly, this half of energy, half a photon's energy cannot be transferred. Photon's energy cannot be transferred in a fraction. Okay, so the similar thing occurs when it goes back to the in ground level. So let's say when it is a star, its energy is E2. It also has to be released an equal amount of energy to goes back to the E1 state, right? The A state. This is my E1. So again, as this half amount of photon energy cannot be released, so it does not fall into this A state. Okay, it does not fall into this A state. Okay, but so this change in energy is actually proportional to the frequency. How? Because when you see this energy gap, this is just a energy balance. That is, what is the energy difference between A star and A? It's A is new. So E2 minus E1, basically the is new. So basically, energy gap is proportional to the frequency. Okay. Okay. So again, that means when let's say this system wants to go to 2 to 3 states, as this energy gap is actually less than this 1 to energy gap. So low frequency photon will be needed. From 3 and 4, energy gap is again decreasing. So that means again low frequency of photon is required. Okay. Now we'll see what will happen if the energy levels are continuous. So in terms of discrete level, we have seen that we need some discrete value of frequency or discrete value of energy, right? So that means if we, let's say, so I'm viewing it. Let's say we want to this, we have a particle in this state 1, and we want to push this particle in the excited state E2. So we need the frequency, let's say h nu 1. Okay. So again, if we want to move the particle from 1 to 3, let's say we need the energy h nu 2. To push the particle from 1 to 4, we need the energy h nu 3 amount. Okay. Definitely here, this h nu 3 greater than h nu 2 greater than h nu 1. Okay, as the energy gap is increasing, and we have seen the energy gap is equal to your energy of the photons that it absorbed. So again, so what we have seen again, when this molecules, when this species get back to the ground state, this same amount of energy is released. So what we will see, if we thought the, let's say, intensity versus frequency, we will only see these 3 discrete values, right? 1, 2, and 3. This is nu1, this is nu2, this is nu3, right? In between this nu1 and nu2, no values are allowed. In between the nu2 and nu3, no values are allowed, right? So this actually tells about the discrete nature of the energy level. The discreteness in the spectrum Spectrum is nothing but intensity versus frequency relationship, by the way. So when we got the discrete values of discrete values of frequencies or wavelength, we will intuitively tell that the energy levels of the systems are discrete. Okay. Now, what will happen if the energy levels are continuous? Continuous means the successive energy gap between two successive levels is very, very low. Okay. That means continuous means delta E, that is energy gap between two successive levels, tends to 0. So in this case, will we see again this discrete spectrum? No. In this case, we will see the continuous spectrum. The spectrum is continuous. The wavelength that is absorbed, it absorbs all kinds of frequencies, because as this energy gap is low, let's say from here to here, we need a frequency of mu1. Again, from here, as this gap is low, from here we need the energy gap E2. But as this energy gap is very low, the difference in energy between this neutron mu1 is also very low. Okay, so all the frequency lines will come very closely spaced, as if it will appear as a quasi-continuous or a continuous. Quasi-continuous in true sense, actually. So characteristics of continuous energy level is your spectrum will be continuous, and discrete energy level means we will get some specific value of the frequencies. So now this is actually the case of this discrete energy level we have mentioned till now is in case of black body. But what will happen in case of atom? So let's say, so in my last lecture, actually, before that maybe, we have derived the energy expression of an atom, right? Anyway, let's again derive. Okay. Some blank page. Okay. So I am removing it. Okay. So till this point, we are standing at the point that if energy levels are discrete, we get some discrete values of frequencies. If energy levels are continuous, we will get some very closely spaced frequency lines. Okay. Now, what will happen for the atom? So, should we expect this continuous spectrum, or will we expect the discrete spectrum? Let's derive with the knowledge we have. So, from the Rutherford model, we told that we need a mechanical force balance, right? So that is your centrifugal force is equal to Coulombic attraction between nucleus and electron. Let's say we are taking with hydrogen atom, 1 electron, 1 proton. So that is 1 into E and 1 into E by R square. So from here, the required velocity is expression of the velocity that will become that cancelled. Okay, it will be E by root over 4 pi epsilon 0 E mark. Okay. Now, what is the total energy? It's a kinetic plus potential energy. Okay, we know this potential energy between electron nucleus is minus E square by 4 pi epsilon 0 r plus kinetic energy is half mv square. If we put the value of this v here, it will be minus e square by 4 pi epsilon 0 r plus plus half m into e square by 4 pi epsilon 0 in r. So that means total energy is minus e square by 8 pi epsilon 0 r. So in from classical mechanical calculation, any radius, there is no restriction on r, right? R is the radius. So this is the only variable here, right? So there is no restriction on r. So that means energy would, there is no restriction on the value of the energy. If there is no restriction on the value of energy, that means energy level is continuous, and we should get this continuous spectrum. Okay, but we don't see that. So when we analyze a spectrum of a hot gas, so we will got some discrete lines. Okay, so but this is got a discrete line. I already told you discrete lines like this. But what is expected from our calculation that we could get the continuous spectrum. All values of both things are possible, which is not the case in case of atom, which is the atomic spectrum. Okay. So anyway, now that I have just given another example, what is the example of continuous spectrum? It is our solar light is an example of sun rays is an example of continuous spectrum. All of them are there, PGR, right? Similar for this incandescent lamp. So so when we analyze the spectrum of hot gas, or that means the gas which contains the atoms, we get the atoms got what is happening here. These atoms got excited. So when it goes back to this its lower energy level, it emits a radiation, and we got this spectrum. That's we call this emission spectrum, right? We have already told in that case that okay, when it got excited from high level to low level, it releases an energy. So here we got this discrete spectrum, which should not be the case. So this is actually very shocking news to the scientist community at that time, because uh, it is beyond their beyond their thinking. That okay, so atoms, uh, they are shocked. They are shocked to see that okay, atom has discrete energy levels. Okay, so what? So they are trying to fit their ideas to explain this position of this spectrum. So what they told that okay, so so that means there is a nucleus and that is an electron, right? Electron is moving around this nucleus. So if nucleus moves, it definitely has some frequency, right? Have some frequency. What is the frequency? It's basically V by 2 pi r. It's velocity by 2 pi r. It's called classical. Okay. Classical frequency is given as velocity by 2 pi r. The distance is covered. Okay. So so they told that okay, as electron is revolving around this nucleus, so the frequency that it will emit should be this any multiple of this nu. Okay, any multiples of this oscillating frequencies of this due to the revolving of the electron. So it should be like mu, 2 mu, 3, etc. So but when we see this position of this peak, is actually follows this principle called Rayleigh's principle. Okay, so so here R is called Rydberg constant. This is just to explain. This is wave number basically. So wave number fits this formula. So this is to explain this position of this lines. Rydberg constant. And here a and n both are integer, and a greater than n. Sorry, a less than n. Yes. Less than n. So it's called a Ritz combination principle. The value I forgot actually. I will tell you in the next class. So by the way, so that means the classical physicists that who are trained classically were thought that try to fit their explanation saying that okay, the electrons, the peak positions or frequency positions should be the integral multiple of this fundamental frequency of the electron, oscillating frequency due to the revolving of the electron. But actually it is not fitting. So that means this. So what is the indication of it? It is the indication that atoms might only have the only specific energy levels, right? Because see, when this again, this is also clear from this expression. This when as n and a have only integer value, so that means definitely it possesses restriction on the value of lambda, and so as the value of frequency and the energy. Okay, so this is an indication that atoms only have some specific energy levels. Not it is not the its energy level is not a continuous thing as we have expected. So something also has to be incorporated in our this energy expression. So we need to think atom in totally different way. So that attempt was first made by scientist Niels Bohr, which we learn in the next class. So I hope you have enjoyed my classes. You have enjoyed my class. And if you like my videos, please like, share, and subscribe. I have actually tried to explain everything in detail. It may not be that shortcut video that you use, that you people watch in the YouTube. Try to explain everything in detail so that you understand all the things, so that you don't have to memorize anything. So that's it for today. And please like, share, and subscribe.